Okay. Well, in the first hour, we have talked about the example about the FIR filter design. And we said that we have information about the passband edge frequency, transition width, stop-band attenuation, and sampling frequency. Of course, to solve any problem regarding to the filter design, first of all, you have to draw the tolerance scheme. Without drawing the tolerance scheme, you will do nothing. Okay, so first of all, based on the given information, we have to sketch the tolerance scheme. After that, you may determine the required values. Yes, it's okay, good, connected. Well, now we said that we have passband frequency, which is 1.5 kilohertz, transition width equal to 0.5 kilohertz, stop band attenuation greater than 50 dB, sampling frequency is 8 kilohertz. Now, based on the information given, let us sketch the tolerance scheme. Of course, here we are talking about what? About a low pass filter. And by now, let us determine the tolerance scheme. Look, please. Now, as you have given the passband frequency is 1.5 kilo. Okay, passband edge frequency is 1.5 kilo. You may write it F in kilohertz. Okay, F to be in kilohertz. Now, so FP is 1.5 kilo, and the transition width, as you can see, is 0.5 kilo. What does it mean? It means that this point, okay, this point will be 2 kilo, okay, 2 kilohertz. Well, 2. Look, passband region is 1.5 kilo. Transition width is what? Is 0.5. I mean, this area will be 0.5. I mean, the second region, the transition width is 0.5 kilo. So the stop band edge will be 2 at 2 kilo. Good. Now, of course, to solve this problem, it requires, we said that ideal impulse function and window function. Two functions are required to solve such a problem. And in ideal impulse response, we have to determine what? We have to determine the cutoff frequency. We have to determine the cutoff frequency. Why? Because the ideal impulse function, look please at the ideal impulse function, edge d of n equals to what? Equals to 2fc sine n omega c divided by n omega c. So what is the missing factor here? Just the fc. Of course, when we talk about fc, you have to talk about normalized fc. Normalized fc. So we are going to use fc dash. Okay, fc dash. fc dash equals to fc divided by fs. Now, all values of the tolerance scheme will be normalized by the sampling frequency. It's good. Now, what will be the value of the FC? Look, please, we said that the FC will lies in the midway between the pass band edge and the stop band edge. So the FC is not given in this problem. So you have to determine it. Now, this will be the value of FC, okay? Which is what? Which is FP plus TR over 2. So it will be 1.5 plus 0.5 divided by 2. So it will be 1.5 plus 0.25, and it will be 1.75 kilo. This will be the value of FC. Now, from the tolerance scheme, we have what? We have determined the value of the cutoff frequency. Okay, so tolerance scheme is very important. Now, the equation, the equation of HD of N will be written as follows. Look, instead of saying 2FC, all of them will be 2FC dash, omega C dash, omega C dash. What does it mean? We are going to substitute FC dash. Now, after calculating the cutoff frequency, FC dash will be 1.75 kilo divided by 8 kilo. And in this way, you can determine the value of the cutoff frequency. Well, now, after finding out the value of the cutoff frequency, now we will be able to determine other values. Now, of course, 1.75 divided by 8 will be about 0.2. Yes, 0.218. Okay, 0.218. It will be 0.21875. This will be the FC dash. Now, after determining the FC dash, so this equation now can be obtained easily. How? All of things are known. FC dash and omega C dash. Omega C dash will be 2 pi FC dash. So just the missing factor is n. Really, I'm going to determine HD of 0, HD of 0, HD of 1, HD of 2, and so on. Of course, how we are going to determine the values of HDs? I mean HD1, 0, HD, yes. How we are going to determine these values? Just substituting n, okay, by taking n equal to 0, 1, 2, 3, 4, 5, up to, say, for example, 20, 50, and so on. Just you have to keep in your mind something. Whenever you are going to determine the values of HD of n in this equation, directly convert your calculator to radian, okay? Put your calculator into radian mode, not into degree mode, and find out the values of HD of n. Again, I'm talking about your calculator. The calculator must be set on what? On radian mode. Now, up to this point, we have what? We have prepared the ideal impulse response. I mean, the FC dash is calculated, so directly we can substitute the value of FC dash in the equation of the ideal impulse response. Remaining will be what? The remaining will be the window function. Well, now, what about the window function? The window function really, we said that based on the stop band attenuation must be greater than 50 dB. So going back to the table of windows, we said that the Hamming window will satisfy the condition of the desired filter. Now, the equation of Hamming window will be as follows. Look, W of n equals to 0.54, okay, plus 0.46 cosine 2 pi n over what? Over n capital. Now, n capital is unknown for us. N capital, which represents what? The number of filter coefficients, okay? Represents the number of filter coefficients. So how we are going to get this value? We said that in the column number 2, okay? In column number 2, the normalized transition width is equal to 3.3 over n, okay? Which is delta F. Delta F equals to 3.3 over n capital. Of course, how we are going to determine the value of delta F? Delta F can be determined by what? Look, delta F equals to transition region divided by what? By the sampling frequency. Transition region is 0.5 kilo divided by 8 kilo, okay? This will be the value of the transition region, and it will be 0.0625. Now, easily we can what? We can substitute this quantity in this equation. So we have the following: 0.0625, okay, equals to 3.3 over n. And in this way, n can be calculated, and n equals to 52.8. I mean, it is 53 coefficients, okay? So how many filter coefficients we have in this example? We have 53 coefficients, starting from edge of 0 and ending by edge of 52. Now, again, we have determined the n capital. N capital again is determined. So now directly we cannot substitute the value of n capital. Okay, the value of n capital now can be substituted here. Okay, and to determine the window function. Now, let us go back to the slides and to continue the example. Well, after we have selected the suitable kind of ideal impulse response, HD of n for the low pass filter, and selecting the suitable window function, and we have determined the missing parameters. In the ideal impulse response, the missing parameters is the cutoff frequency, and the missing parameter in the window function is the n capital, I mean the number of filter coefficients. Now we will be ready to complete the question. Okay, look, this will be the low pass filter, and window function again is determined. So what we are going to do at the end of the day, just substitute HD of n, take n from 0 up to, say, for example, 26, and the same thing for window. Find the values of the window function from 0 up to 26, and we have symmetry between the values. Look, please, edge of 0, edge of 0, edge of 0 up to edge of 26, and edge 26 up to edge of 52. They are what? They are similar, okay? They are similar. We have symmetry between these values. Why we are looking to find out the symmetry between the filter coefficients? To get what? To get and to ensure that the phase of the filter is linear. This is about what? About the solution or finding out the filter coefficients using the window method. Okay, up to now we have talked about what? About the design of the filter using the window method. Now we have another kind of windows, I mean of filters, sorry, which will be the IIR filter. Now, IIR filter design. Now, to design now the IIR filter, we have basically 3 techniques. First technique is called the pole zero placement method. Second technique is called the impulse invariant method, and the third one will be the bilinear Z transformation. Now, let's talk about the first technique, which is the pole zero placement method. Of course, how we are going to design an IIR filter. We have some steps we have to follow. First step is what is the requirement or filter specification, at which stage the designer, the designer will give you for example, the requirement of the filter. For example, low pass filter, high pass filter, amount of pass band ripple, amount of stop band region, and so on. Now, step number 2, approximation or coefficient calculation. Of course, to find out the filter coefficients in the IIR filter, we have techniques. First technique we said will be the pole zero placement. Second, impulse invariant, and the third one will be bilinear Z transformation. Now, in FIR filter, we have edge coefficients. I mean, H0, H1, H2, H3, H4, H5, and so on, up to say, for example, H50 and so on. No problem. Now, when we are talking about the design of IIR filter, now we have different story. Why? In IIR filter design, we have two kinds of coefficients, AK and BK coefficients. Well, in the FIR filter, we have only edge values we are going to calculate. We said H0, H1, H2, and so on. Now, in the case of IIR filter, now we have different values. Okay, I mean A and B coefficients. So we are going to determine two kinds of coefficients, which are AK and BK. Of course, these two coefficients relates to the numerator and denominator of the edge of Z function. Now, realization simply converting the transfer function into suitable filter structure. Really, we are going to talk about what about representing the filter by some delays, multiplication, addition, and subtraction operations. Point number 4, analysis of errors that would arise from representing the filter coefficients and carrying out the arithmetic operation involved in the filtering with only a finite number of bits. Of course, this point is very important. Why? Now, for example, as you know, whenever we talk about any digital system or any microprocessor, any microcontroller, any DSP kit, we are talking about a digital system or a digital control circuit. Of course, any microprocessor, microcontroller has limited number of bits. I mean, when we talk about the registers of the microprocessor, say you have a register of 32 bits, 64 bits, 16 bits, 8 bits, and so on. So you have what? You have limited number of bits in of the, I mean, length of registers. In other words, when you are going to represent numbers, we are what? We have to be restricted with this limited number of bits. Thus, sometimes when you are going to design filter, we may have filter coefficients which will be, for example, consist of, say, 0.66667. For example, we have after the floating point, say we have 5 digits or 3 digits. Well, of course, due to using limited number of bits, at that time we are going to what? We are going to approximate the filter coefficients. This approximation or quantization of the filter coefficients will lead to what? Will lead to the degradation in the filter performance. So this step, I mean step number 4, is very important really to implement the digital filters. Now, point number 5, implementation, which involves building the hardware and or writing the software codes. and carrying out the actual filtering operation. Now, sometimes we may implement the filter using a software program like MATLAB, C, Python, and anything else, or sometimes it requires software with a hardware. Okay, so sometimes hardware and software there's cooperation between software and hardware to perform the filtering objectives. These stages are summarized in figure 7.1. 7.1 really represents the flowchart of the filter design: performance specification, calculation of the filter coefficient, realization, finite word length effect, which is the step number 4. I mean, talking about the quantization of the filter coefficients. And finally, we have hardware and or software implementation plus testing, and this will be the steps for designing an IIR filter. Now we have calculation of IIR filter coefficients. Of course, we are going to talk about the techniques, methods, algorithms that can be used to determine the filter coefficients. The task at this stage is to select one of a number of approximation methods and calculate the values of the coefficients AK, BK in equation 7.2, such that the filter specification given in stage 1 are satisfied. A simple way to obtain the IR filter coefficient is to place poles and zeros judiciously in the Z plane such that the resulting filter has the desired frequency response. This approach is only useful for very simple filters. For example, notch filtering and bandpass filters. Now, please, to understand what's going on in this technique, you have to beware for this slide. Now, in the previous lectures, we have talked about zeros and poles of any, say, Z functions, for example, x of z or h of z. We said that zeros means what? Means the roots of the numerator. And if you are going to substitute these values in the x of z or h of z, will make the equation equal to 0. Well, poles, on the other hand, if you are going to substitute in the h of z or x of z by the values of p, I mean the poles, will lead that the function or the h of z will equals to what? Infinity. So we have two important parameters in any x of z or h of z, which are what? Which are the zeros and poles. And we said that zeros represent the roots of the numerator and poles represents the roots of the denominators. Well, look please, here we have a diagram, this simple diagram, and as I have told you before, 0 is denoted by a small circle and pole is denoted by a cross. Okay, a cross. Of course, as you can see here, we have two poles at the imaginary axis, okay, at fs over 4. So due to the pole, we have what? Maximum values, okay, while zeros will lead to what? Will lead to minimum values. Look, this will be at 0. At 0 you have 0, and at 180 degree again we have what? Another minimum. So the location of 0 will be reflected on what? On the spectrum or the magnitude spectrum of the filter. So whenever you are going to put a 0 at a specific location on the unit circle or on the pole 0 diagram, it will generate a magnitude spectrum filter with the requirement as we can see in the next coming examples. Now, an important point. Again, we have a very important point and hint. An important point to bear in mind, okay, is that the coefficients of the filter to be real. We have said that we have two kinds of filter coefficients here, AK and BK filter coefficients. So if you are going to we have to ensure that these coefficients are real. We have to have the following. the coefficients of the filter to be real, the poles and zeros must either be real. What do you mean by real? They lie on the real axis, or positive or negative real axis, or occur in what? Or occur in complex conjugate pair. Well, this is the very important point. Now, of course, this lecture will be finished by this example. Okay, I'm going to talk about the solution of this example, and in this example you will be learned how we are going to design a filter using the pole zero placement method. So let us at the beginning read the example. A band pass digital filter is required. Well, so in this example, we have what? We have a band pass filter. A band pass digital filter is required. Well, what are the requirement of this filter? Of course, it will be complete signal rejection at DC and 250 Hertz, narrow passband centered at 125 Hertz, a 3 dB bandwidth of 10 Hertz, and again, keep in your mind that the sampling frequency is 500 Hertz. Well, so we have the following information. Complete rejection at DC and 250 Hertz, narrow passband centered at 125 Hertz, a 3 dB bandwidth of 10 Hertz. Okay, these are the requirements of this example. Again, the sampling frequency is given by 500 Hertz, yes, or samples per second. Now, of course, let's go to the whiteboard to make the complete solution for this example. First of all, again, we have to what? We have to make a sketch for the tolerance scheme of the desired filter. Yes. So, first of all, let us make a sketch for the desired filter. Now, based on the requirement, here we have the following band pass filter. Look, please. We said that we have complete what? Complete signal rejection. I mean, the signal values will be 0 at DC. Of course, DC means 0 Hertz, and at 250 Hertz. Now, what will be the peak? A narrow passband centered at 125 Hertz. So this will be the point of 125 Hertz. Okay, now to discuss this problem, really, look at the example. This will be F, and this is the edge of F. Well, edge of F. Now, please look. At DC and 250, we have complete signal rejection. So what we are going to do, we are going to put zeros. Okay, put 0, and again, put another 0 at what? At 0. Well, what's the maximum value? Maximum value occurs at 125 Hertz. So at this point, we are going to what? We are going to put a pole. Okay, location of pole and location of zeros by now are determined. Now, again, keep in your mind that the sampling frequency Fs is given in the problem by 500 Hertz. Oh, it's good. Now, let me explain how we are going to determine the values. Please, when we talk about a zero or a pole, they are what? They are vectors. Well, zeros, okay, and poles are what? Are vectors. Of course, when you talk about vector, you know that what I mean by vector. Okay, they are what? They are vectors. Vectors, each vector is represented by two quantity, magnitude and angle. Well, every vector is characterized by two parameters, which are the magnitude and what? And the angle. Look please by now. Now we have two zeros. I mean Z1 and Z2. Okay, Z1 and Z2. And Z1 will be what? Magnitude of Z1 with angle of Z1. Z2 again will be magnitude of Z2 and angle of Z2. Same thing for P, okay? We have a maximum value occurs at what 125 hertz. So we have P1 equals to what? Magnitude of P1 and angle of P1. Well, of course, whenever we are going to finish the calculation of the values of the vectors Z1, Z2, P1, P2, at that time, edge of Z will be as follows. Look, please. Edge of Z will be Z minus Z1 multiplied by Z minus Z2 divided by Z minus P1 multiplied by Z minus P2. Okay. By now, as I think you have become familiar with the topic. Now, so the missing parameters in this edge of Z will be what? Will be Z1, Z2, P2, P1. Okay, so you have to use techniques by which to determine these values. I mean Z1, Z2, P1, and P2. Now, first of all, let us talk about the Z1. Of course, Z always in the design of the IIR filters using the pole zero placement method, the magnitude of Z1 equals to the magnitude of Z2 and equals to 1. Okay, magnitude of the zeros to be considered 1. So it's very simple and easy. The remaining is what? The remaining is to determine the angle of each zero. Of course, the angle of each zero can be calculated as follows. Look, please. Angle of Z1 will equals to 360 degree multiplied by 0 divided by the sampling frequency. Of course, as you can see here, the angle will be 0. Well, now, the angle of Z2 will be 360 degree multiplied by 250 divided by the sampling frequency, which is 500. Now it's very clear that it will be 180 degree. So the direction, the angles of the Z1 and Z2 is easily determined and obtained. Now Z1, after this calculation, now look please, Z1 will be 1 and its angle 0. Z2 will be 1 and its angle 180 degree. So the numerator of h of Z is calculated. Remaining is what? The remaining will be the denominator of the h of Z. I mean P1 and P2. Now, let's go to the what? To the P2 and try to calculate the P2 or P1. Okay, now P1. P1 again consists of magnitude of P1 and angle of P1. Let's go to the tolerance scheme diagram. Look, please. The pole, I mean the maximum value, occurs at what? At frequency of 125 hertz. So how we are going to determine the direction of this value? Again, using the previous equation. So the angle of P1 will be 360 degree multiplied by 125 divided by 500, and it will be 90 degree. It's good. Now, What about the length of P1? Length of P1. Really, we have an equation which is calculated based on the practical applications. R or P1 magnitude. Okay, P1 magnitude. P1 magnitude equals to R, and R equals to 1 minus bandwidth divided by Fs multiplied by pi. Okay. In the question again, in the example, we said that the bandwidth of the filter, is 10 hertz. Okay. Now, where is the bandwidth? Let us select the bandwidth. Okay. This will be the bandwidth, and it's a very narrow bandwidth. Okay, it is what? It is 10 hertz. So based on the following information, we can determine what? We can determine the value of R. So directly, R will be 1 minus 10 divided by 500 multiplied by pi, and it will be about 0.937. 0.937. So in this example again, I mean P1 is equal to 0.937 as a magnitude, and its angle will be 90 degrees. Now, please, let's plot the pole zero for this example. Now, let's talk about the pole zero diagram. I'm sorry, it's not correct. Yes, in this time. And I'm going to draw a circle. Look, please. Here we have a circle. Good. Now we are ready to continue with the problem. Look, please. We said that we have a zero which has a length of 1 and its direction equal to 0. So this will be the first zero. Second zero again, its length equal to 1, but its direction will be 180 degrees. So it will lies at this point. Now, what about the pole? We said that the pole has direction of 90 degrees, and its magnitude, as you can see here, its magnitude about 0.937. So it will be very near to the what? To the circumference of the circle. Okay. So this will be the location of the what? Of the pole. Now, look please at this important point. This will be very important point now. We said that in previous slides, a very important note, and we said that you have to keep this information or this note bear in your mind. To get real coefficients of the IR filter, the pole zeros, okay, of the filter either lie on the what? On the real axis. Now the zeros are what? Lying where? On the real axis, or they have to obtained as complex conjugate. By now, using the information given in the problem, all we need is what? A single pole. But this pole will lie on the what? On the imaginary axis, and it's not a complex conjugate. This will lead to what? This will lead to complex values for the what? For the coefficients. If we are looking for real values coefficient, we have to what? We have to add another pole in the other direction. I mean, it's complex conjugate. So we have another pole with what? Called P2 equals to 0.937 with angle equals to minus 90 degrees. And this one will be what? Will be 0.937 with angle equals to 90 degrees. So P2, I have added the P2 for what? To get complex conjugate poles. So at the end of the day, we will get real coefficients of AK and BK. Well, now, after that, now we have determined the value of Z1, Z2, P1 and P2. Now we can easily write down the edge of Z. Now look please, edge of Z will be z minus z1 multiplied by z minus z2 divided by z minus p1 multiplied by z minus p2. Now substitute the values. This will equals to, as you can see, z1 will be 1, y angle is equal to 0. So z minus 1 multiplied by z plus 1, y, we have 1 and angle of 180 degree, so it will be minus 1, divided by z minus 0.9, sorry, 0.937 e to the minus j pi by 2, and z minus 0.937 e to the j pi by 2. Well, so this will be the two poles. Now, what we are going to do for the other steps, we have to simplify this equation. Of course, to simplify this equation, you have to use this formula, please. E to the j theta will be what? Will be cosine theta. Of course, if you have a plus and minus, minus a plus, okay, cosine theta minus a plus j sine theta to simplify the equation. And then you can multiply and simplify the whole equation. Now, edge of z will be z squared minus 1 divided by z squared plus 0.877 969. Up to this point, we have what? We have obtained the edge of z, which is the requirement of this problem. Now, next step is what? Of course, I'm going to ask you about the difference equation of this filter. Well, difference equation of this filter. Of course, to obtain the difference equation of this filter, you have to what? You have to express the edge of z in terms of negative exponents. So I'm going to multiply numerator and denominator by z2 minus 2. Now, edge of z becomes 1 minus z2 minus 2 divided by 1 plus 0.87796 z2 minus 2. Now, in the previous lecture, again, I have told you that the transfer function is composite of y of z over x of z. Okay. Now look, please. Edge of z can be expressed as y of z over x of z, and it will equals to 1 minus z2 minus 2 and 1 plus 0.87796 z2 minus 2. Now I'm going to multiply and going back to the x of z and y of z, one of them to the right side and the other will be to the left side. So y of z will be multiplied by 1 plus 0.87796 z2 minus 2 equals to 1 minus z2 minus 2 x of z. Now, expand the brackets. Now it will be y of z plus 0.8779 z2 minus 2 y of z equals to x of z minus z2 minus 2 x of z. Now you can determine the inverse z transformation by inverse z transform. We have y of n plus 0.8779 y of n minus 2 equals to x of n minus x of n minus 2. So in this way, we have what? We have obtained the difference equation. Look, please, we are going to finish the example. Now, y of n will be minus 0.8779 y of n minus 2 plus x of n minus x of n minus 2. Well, this will be the difference equation. Now, the final stage for this example will be what? Will be the realization. I mean, converting the difference equation into what? Into delays and addition and subtraction operations. Now, please look at the difference equation. I'm going to construct the realization or diagram based on the what? Based on the difference equation. Now, to do so, first of all, we have to specify the input and output of the system. Input is x of n, and output will be what? Will be y of n. Of course, in between, we have a summing circuit. Okay, this will be a summing circuit. Well, now, as you can see here, we have x of n. Okay, x of n, this will be, and x of n minus 2. So how we are going to realize x of n minus 2? Of course, by z to minus 1 means what? Delay by one sample. Again, z to minus 1, delay by another sample. Just let me illustrate it well. Okay, now, again, this one is z2 minus 1. So at this point, okay, it will be what? It will be x of n minus 1. At this point, we have x of n minus 2. Okay, x of n. Just give me x of n minus 2. Well, now we are going to feed this one to whom? To the system. Of course, in negative. Okay, in negative. Look, x of n, this will be x of n, and x of n minus 2 will be this one. And it is in negative, so it has negative sign. Well, now, let's go to the y side. Okay, now, the output of the summation represents what? Represents the y, but we have a feedback from the y. Look, please, here we have again y of n minus 2, y of n minus 2. So I am going to take a line from y, delaying by one element. It will be y of n minus 1. Okay, this will be y of n minus 1. And another delay we have, again, z to minus 1. Again, it will be y of n minus 2. But in this time, y of n minus 2 is scaled by minus 0.8779. So here we have a scaling function, okay? A scaling function. This will be fed to a scaling function. Its value will be minus 0.8779, and again will be fed to the summing circuit. Of course, this will be the realization of this filter again. Now, in this lecture, we have talked about the design of the IIR filter using the pole zero placement method. After that, we have obtained the edge of Z, I mean filter transfer function. Then from the edge of Z, we have obtained the difference equation. And then based on the difference equation, we have realized the filter using the direct form realization. This is about the lecture of today. Still, I want to tell you something. We need another hour, okay? Just 1 hour I need to talk about the design of the impulse invariant filter and bilinear Z transformation. Of course, you have to prepare yourself for the quiz of the Wednesday. The quiz will be about the Z transformation and its inverse, with, of course, with initial and final value properties. Now, do you have any question, please? Huh? Do you have any questions?
I think there's no question. Thank you, sir.
Okay, so please on next Wednesday. Okay, and next Wednesday you have to read carefully. Okay, the Z transformation and its inverse. It's a good chance for you to get and to collect good marks. Okay, so good luck and see you inshallah next Wednesday inshallah. Thank you very much.